Well, welcome back, ladies and gentlemen. We are going to start today with, well, it's a pretty deep and complex topic, if I'm perfectly honest with you. We're going to be talking about electron configurations. If you remember from the last couple of videos, we found out that light exists as both a wave and a particle, and that the electrons do not exist in orbits that go around the nucleus like what's shown in the video here, but rather they exist in three-dimensional regions known as orbitals. Now, what we're going to look at today is how do we identify which electrons are in which orbitals, and within an element be able to tell which electrons are in which specific orbitals. So it's going to take a bit of time to get through this material. Hope you've got a good drink handy, got some snacks, you're ready to rock and roll. So let's begin. So our goals today, hopefully you will be able to understand how electrons function within an atom. You should be able to determine the electron configuration of any atom, and then also be able to use the electron configuration and noble gas notation to determine the number of valence electrons in an atom. So our real big focus today is on those electrons, and how do we determine which particular orbitals those electrons are located in. We have a few key vocab terms for today. That includes electron configuration. We'll also talk a little bit about the Pauli Exclusion Principle, noble gas, valence electrons, Aufbau Principle, Hund's Rule, and noble gas notation. All of these will be very important when we try to go through and figure out what are the notations that we're looking for in this particular video. If you remember from our last video, we talked about 4 different quantum numbers, and those quantum numbers identify the specific locations in which electrons are located. Well, what's fortunate is that the periodic table is set up in a way where we can determine where those electrons are going to be located based on the element's location on the periodic table. So keep in mind the unique electron configuration exists for each element. Each element contains a different number of electrons, and therefore will have a specific configuration on where those electrons are located. So it's a bit confusing, but I'm going to go through and explain to you a little bit about how the periodic table is set up, and then we're going to go through and be able to identify where those electrons are located in any particular atom. Okay, so what I've done here is I've provided you with an image of the periodic table on this show. The first thing we want to look at is the energy level. Now, energy levels are pretty straightforward. They just simply are represented by the period that the element is located in. So this first row up here, this is the energy level 1, and then this is energy level 2, 3, 4, 5, 6, it's a bad 5, and 7. Now, if you take a look down here on these parts down here at the bottom, notice that there are extensions of 6 and 7. The atomic numbers go 55, 56, 57, and then down to 58. So this is considered energy level 6, and this one energy level 7 as well. The next thing we need to look at are the sublevels. Okay, keep in mind that each sublevel has a different shaped orbital. Okay? So what's nice is the periodic table is actually broken down in a way where it's pretty easy to determine the sublevels, and they're all given by letters. So for this particular activity, we're going to take helium and actually move it over here. Makes it a little bit easier to understand what we're looking at. Okay, so we're just going to get rid of that over there. All right, so the first 2 rows here, this is known as the s orbital, and if you remember from our previous video, we talked about how s sublevel orbitals are shaped like spheres. Okay, each has one orientation. Okay, and each orientation holds 2 electrons. Okay, and it makes sense because the column is actually too wide. So this H here would hold 1 electron in the 1s orbital. This one here is going to hold 2 electrons in the 1s orbital. Okay, because remember, helium, 2 protons. In the neutral atom, to balance it out, it would have 2 electrons. Okay, so that's the s orbital. If we move all the way over here, these are known as your p orbitals. I'm sorry, p sublevels. Okay, and with this, there are 3 orientations. Okay. Well, since there's 2 electrons in one orientation, in this one there would be 6 electrons. And it makes sense, right? Because the column's 1, 2, 3, 4, 5, 6. So there's 6 electrons here. If I have neon, I have all 6 electrons in that orbital. If I have boron, I just have 1 electron within that orbital. Okay, so make a little more sense on how we orient these as we move through the process. Down here, in between the S and the P, we have our D block, or our D sublevel. And the D sublevel has 5 orientations. And you guessed it, there will be 10 electrons in this sublevel. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then the last one down here at the very bottom, I'm just going to kind of draw an arrow out here. This is your F sublevel. And if you've noticed a trend here, we've got 1 orientation, 3, 5. This one's going to be 7. And with a total of 14 electrons possible in that level. Again, there's 2 electrons for each orientation. So you have 14 elements that go across each particular F block. Okay? So when we go through and we identify, which orbital or which sublevel that they're in, we use the energy level, we use the sublevel, and then we describe just how many electrons are in there. So for example, with hydrogen, again, if we wanted to know hydrogen's electron configuration, we would say that it is 1 for the energy level, S for the sublevel, and 1, because that's how many electrons are within that sublevel. If we wanted to know helium, for example, helium still, again, in the 1s, but because it has 2 electrons, it's number 2 on the periodic table, we say it is 1s2. Okay? Now, these are going to be cumulative, meaning that when we describe a higher level of energy, we have to describe that the energy level before it is full. So if we remember, in the 1s energy level, 2 electrons make it full. So let's describe lithium here. Lithium is beyond the 1s orbital, which tells us that it is full. So we describe lithium as 1s2, but notice it is in the next energy level. So we would describe the next energy level down as 2s, and then there's only 1 electron in there, so it'd be 2s1. Okay? We continue on. Beryllium, same thing. We have a variety of energy levels here. We are past the 1s orbital, so we describe that as 1s2. And we are in the 2s orbital now, but instead of just 1 electron in the 2s, it has 2. One thing to keep in mind, and a way to kind of help you remember this, is that your superscripts, your exponents up at the top, when you add them up, if it's a neutral atom, they will equal the atomic number. So 2 plus 2 is 4. Makes sense, right? Let's do oxygen. Okay. So again, we're past the 1s orbital. The 1s is full, so 1s2. We're past the 2s orbital. That one's full, so that is 2s2. Now we go to the next one. So this next orbital will be 2p. How many electrons are we into the 2p orbital? 1, 2, 3, 4. So that would be 1s2, 2s2, 2p, 4. That describes the electrons that are located within an atom of oxygen. Okay? Now that breaks down most of this. The only other little tricks that are here are when we get into the d and the f orbital. So with the d orbital, because there are so many electrons within the d orbital, it actually pulls them closer. So we don't actually consider this energy level right here to be 4d. We actually take the energy level for d and we subtract it by 1. So this is technically the 3d orbital, this is 4d, and this is 5d. Okay? So that's kind of a little bit tricky there, but your d orbitals are always going to be 1 less than the actual energy level that it's in. F works in a very similar way, except with the f orbitals we subtract 2. So this level right here is actually 4f, and this one right here is 5f. Okay? So I know that there's a lot to remember here. There's a lot of writing that's on this. We will practice with this, but I just want to give you a good idea of what exactly we're going to be looking at when we describe electron configurations in an atom. So kind of an easy way to remember the way in which the orbitals go, I write them down. So if I look at, you've got 1s, 2s, 3s, 4s, 5s, 6s going down the left-hand side here. Notice that in the diagram previously shown that there is no 1p, there's no 1d, there's no 1f. Okay, so you kind of write it in a diagonal, and then you use diagonal lines going across the opposite direction. So we start off in the 1s orbital. When that becomes full, then electrons are in the 2s orbital. When we're done with that, we go to the 2p, then the 3s, then the 3p, the 4s, remember the 3d, 4p, 5s. It works across the periodic table, but again, utilizing something like this might help you understand the exact order in which it goes. So a couple of key rules, a couple of key principles that we want to look at here. One is known as the Aufbau Principle, which states that the electron will occupy the lowest possible level that it can. It's all about being energy efficient. So electrons are going to occupy the 1s orbital before they occupy the 2s orbital, because the 2s orbital is a higher energy level. Same thing with 2s and 2p. It will occupy the 2s level before the 2p. So essentially it follows the periodic table of elements going across. 1s and then 2s, 2p, 3s, 3p, 4s, etc. Now sometimes we like to visually demonstrate these electrons. And to understand this better, we use something that's known as the Pauli Exclusion Principle, which states that no two electrons can have the same four quantum numbers. If you remember, the very last quantum number in our previous video talked about spin. So even though there are pairs of electrons that are located inside each orbital, each one technically has a different spin. So they cannot have the same four quantum numbers. And when we draw these out, we draw them with an up arrow and a down arrow to indicate the different spins. Keep in mind here that this particular atom is demonstrative, fancy word there, of an atom of nitrogen. So you see we got 1s2, which is full. It has an up and a down, so that means that it's 1s2. 2s2, again an up and a down. And then 2p3, 1, 2, 3. Now the reason why they're up arrows rather than down arrows is that orbitals that have the same energy level are more energy efficient if they are occupied with one electron before having a second. So that's why the one at the top is correct when we go through and we draw our lines, is that we show 2p3, each one is going to have one electron first, and then we're going to go back and add our second electron. So that explains why the top one is correct and the bottom one is not. Again, we'll take a look at this a little bit more in a later slide. So the question states, show the electron configuration and orbital notation for the following: hydrogen, helium, lithium, fluorine, and chromium. So if you don't have a periodic table out, I would highly recommend you get one out now. So pause the video and get out a periodic table. Do it. Now. I'll wait. Just kidding. All right, so with hydrogen, we know hydrogen is element number 1 on the periodic table. So we follow the periodic table. We know that that is the 1s orbital, and there's one electron in there. That's it. That's the electron configuration for hydrogen. Okay. If we want to show the orbital notation, now that is the one using the up and down arrows. Now to show that, we write 1s, and remember, there's one possible orientation of the 1s. So we just draw one line, and there's only one electron in there, so we draw an up arrow. That's it. So that is the electron configuration and orbital notation for hydrogen. If we go to helium, helium is going to be very similar. We know that it's number 2 on the periodic table, still in the 1s orbital. So this would be 1s2. And that would be our electron configuration. And to show our orbital notation, be 1s, with an up arrow and down arrow. Okay? Lithium is number 3. If we look at it on the periodic table, it is in the 2s orbital, but we need to describe all of the orbitals before then. So we start at the very beginning. The 1s is full. We're past it. So then we show 2s and 1 because there's only one electron in that 2s orbital. Okay? So to draw this out, we have 1s, 2s, and again, up, down, and up. Okay? Fluorine. Fluorine is number 9 on the periodic table. If we look at that, that's actually in the 2p orbital. Remember, we need to write all of our electron configurations before then, so we're going to have 1s, 2. 2s is full because we're past it. We're in the 2p, and if we count up, it'd be 1, 2, 3, 4, 5 electrons in the 2p. So to write this out, you have 1s, 2s, 2p. Remember, this has 1 orientation, 2 orientations. Remember the p, though, 1, 2, 3 orientations, because it can hold a maximum of 6 electrons. So up, down, 1, 2, 1, 2. And remember, this is going to be 5. So 1, 2, 3, 4, 5. I would get in the habit of writing them. Write your up arrows in each orbital before you write your down arrows. It'll make a lot more sense. The next one is chromium. Chromium is number 24 on the periodic table. So again, just follow along. If we're past that particular orbital, it is full. Okay? So 1s is full. We're past that. We go down to 2s. 2s is full. We're past that. 2p is full. We're past that. 3s is full. We're past that. Keep going. 3p is full. We're past that. Go to the next one. 4s is full. We are past that. And then we get into the next. Now remember, d orbitals is our first venture into a d orbital. D orbitals have one less energy level. So we're going to be moving into the 3d orbital. And I count 1, 2, 3, 4. I'm 4 electrons into the d orbital. Now, again, easy way to check. Add your exponents, and if they add up to 24, you did it right. So 2, 4, 10, 12, 18, 20, 24. So we're in good shape here. Now to draw this electron configuration is going to require a little bit more space. So I'm going to go ahead and erase a little bit of this. It's just like using a pen. It's kind of fun. All right, we're going to go back to using our pen here. So we'll start at the very bottom. So we have 1s, 2s, 2p, 3s, 3p, 4s. I'll write this off to the side here to help. And this will be, oh, I made a mistake there. After 4s is 3d. So remember 1 orientation, 2, 1 orientation here. We have 3 here. 1, 3. Again, that's because of their s and p. D, because it has 10 electrons possible, it has 5 possible orientations. And then you just add your up and down arrows. Notice that I'm writing my up arrows before I write my down arrows, making sure that I always use proper notation. And then with D, there are 4. So remember, we write our up arrows first. 1, 2, 3, and 4. Okay? So that is how you would do that. That is your electron configuration and your orbital notation. Now, when we start getting into larger electron configurations, it can be quite cumbersome to write them out. So to simplify that, we actually use what's known as the noble gas notation. Noble gases are elements in group number 18. So they're the ones on the far right-hand side of the periodic table. Things like helium, neon, argon, xenon, krypton, radon, etc. I think there's only one more. I think it's Ogan Son 118, but who uses that? We can write the noble gas notation. So this is kind of like a little bit of a shortcut. By using the noble gas elements enclosed in brackets to represent the electron configuration for that element. So if I look on the right hand side here, I have silver, and silver has a relatively long electron configuration. So in order to write my noble gas notation, I look at the last noble gas I passed. Mr. Lamb said passing gas. You look at the last noble gas you pass, and with silver, if I go back, the last noble gas is krypton, Kr. If I write krypton in brackets, that takes care of all of the electron configuration up to krypton. And then you would just continue on with whatever electron configuration you would need in order to get to silver. In this case, it would be 5s2 4d9. Okay? So the noble gas notation is a great way to essentially get this in some shorthand. So that way you're not writing out really, really long electron configurations. Iridium is number 77 on the periodic table. So because it's number 77 on the periodic table, we're just going to pretend that that's not there, because that's going to royally suck when we try to write that out. Again, the process is still the same, and I may ask you to do one or two of those, but for the length of this video, we're trying to cut that down. So electron configuration, again, follow the periodic table for Iridium. So I have 1s2 full, 2s2 just full, okay, 2p6, keep going, 3s2, 3p6, 4s2. We're going to keep going, 3d10. Remember, d is one less than the energy level in which you're actually at. The next one's going to be 4p6. We go down, 5s2, 4d10, 5p6. And keep going down that periodic table. We're going to go to 6s2. Now, remember, we go down to the F block this time. Remember, the F block is 2. We subtract 2 away from the energy level to get the correct energy level for the F block. So it's actually 4F14. And then it is 1, 2, 3, 4, 5, 6, 7. So this is going to be 5D. Whoa! All right. So there is our electron configuration for Iridium. We end at 5d7. Now, the next thing we're going to take a look at is our noble gas notation. So if we go back from Iridium, we look at the last noble gas. The last noble gas we passed is xenon. So we're going to write xenon in brackets, and that represents the noble gas, that represents the notation all the way up to this right here. So at the end of 5p6, that's where we get to xenon. So now all we do is we just write what's left. 6s2, 4f14, 5d7. And life is good, okay? So the noble gas notation makes writing this a heck of a lot easier than what it would without it. All right, and lastly, we can determine the number of valence electrons in an atom based on its noble gas notation. Valence electrons are the outermost electrons in an atom, and they are the ones that are involved in chemical bonding. So in order to find them, it's pretty straightforward. We just write the noble gas notation, and then we add up the total of the s and p electrons. Keep in mind you will have no fewer than 1 and no more than 8 in the outermost shell of an atom. So here with silver, I just add up the s and p electrons from the noble gas notation. There are 2 s electrons, no p electrons. So I would say the number of valence electrons in silver in this instance would be 2. Whew! That was a long one, okay? But it covers a lot of the really important things we need to make sure we know for this unit. So keep in mind that electrons fill the lowest energy level first. There are a variety of different ways to show electron configuration with orbital notation, noble gas notation, and then from that noble gas notation we can calculate the number of valence electrons. I know it was a long video, guys. I'm going to probably cut this down into 2 separate videos, or maybe just make you guys watch half. Either way works fine. But keep those things in mind, get these notes taken down, and we will take a look at this when we come back next time. All right, have a great day, guys. We'll talk to you later. Bye-bye.